the plan of the lectures is as follows. First, I will define what is complex manifolds, and then I will introduce what are the scalar metrics on complex manifolds, and that will already take me like 1 or 2 lectures, and then I will talk about applications of these scalar metrics. So let's begin with the definition of complex manifolds. So the first part is complex manifolds. So the definition of a complex manifold is as follows. So a complex manifold is given by the following data. So first, we need a topological manifold. So first is so this is Hausdorff second countable topological space, say M. And can you read? Okay. So that's first part. Then we need an open cover of this topological space. So M is a union of open sets. So alpha is my index, lambda my index set. So it's a union of open sets U alpha. And then third and most important, we have, so to say this, U alphas are open. And then third, we have homeomorphisms. So complex manifold is something that locally looks like Cn. So we have homomorphisms U alpha to some U tilde alpha inside Cn. So these are open sets of Cn. And these are homeomorphisms. So then let's have the following compatibility property. So such that so when we calculate the transition functions, so these things are so-called like charts. When we calculate these transition functions, they have to be holomorphic. So the picture is like this. So we have some topological space M, and then we have a cover of the topological space by open sets. Let's say this is U alpha. Then each of these sets is homeomorphic to an open set in Cn. So here we have Cn, and we have the U tilde alpha. And then when we compare these different charts on their overlap, so I have another chart here, phi beta, then the image is another set, U tilde beta, another set, open set in Cn, and then when we compare, so on the that here, we have this transition function. So the transition function maps open set in Cn to an open set in Cn. So this is like so this is transition function, and the key thing is that this is holomorphic. And I will write it again, holomorphic. Key. Yeah.
Would you remind what does it mean to be holomorphic?
Yeah, I was gonna say that after, but so I guess you've seen for maps from if n is equal to 1 is a holomorphic map between sets in C. So there are these Cauchy-Riemann equations. So okay, how so so if you have a function, let's say there is f is a function that goes from an open set. Omega here is an open set in C, and then this function is a function with complex values. So this function has like two real and imaginary part. So u and v are real functions. So, and then holomorphic. So holomorphic means that the function satisfies the Cauchy-Riemann equation. So in C we have like x plus y coordinates. So we have the Cauchy-Riemann equations. So these equations are like partial of u with respect to x is equal to partial of v with respect to y, and partial of b with respect to x is equal to well, minus partial of u with respect to y. So this is holomorphic functions for when the domain is an open set in C. So of course these functions are all like smooth, like C infinity functions. Smooth function. And so this is for functions that go from open set in C, and then there is a straightforward like extension to several variables. So let's say now if this set is in Cn, then you have like n different coordinate functions, set j, and then this function is holomorphic if it is so with respect to each of the variables. So here you, with respect to each of the variables, the function is holomorphic. So so yeah, holomorphic functions are a very special kind of functions, like sort of very, they sit somehow in between like the huge class of smooth functions and the smaller class of polynomials, and holomorphic functions are somewhere in between. It's like not the polynomial, almost a polynomial, but not really. Yeah. So so any questions? So I think most of you might have seen what is the definition of a manifold. Like manifold, it's real manifold, and it's all Rn, and this is differential smooth. And here, the whole difference is in this word, holomorphic. And then the plan of today's lecture is I want to show you how this class of objects of complex manifolds is different from the class of smooth manifolds. So, well, it's a subset clearly. So, it's a subset of smooth manifolds because you can think you can define like a complex manifold is just a smooth manifold with this special atlas. So the collection of all these charts is called an atlas. So we have the atlas is by definition this we call A is the collection of all these charts U alpha phi alpha with alpha in the set. So this is the atlas. So a complex manifold is a smooth manifold with a holomorphic atlas. Here I want to mention on a technical point in the definition is that this atlas that I used in this definition is sort of accessory thing. It's not because once you have an atlas, you can just change. Let's say I can add a constant to this. Yeah, you can add a constant, and you still have an holomorphic atlas. But the manifold is the complex manifold is the same. So actually, two atlases are equivalent if when you compare the charts, the transition functions are holomorphic. And the correct definition of complex manifold is a differentiable manifold equipped with an equivalence class of holomorphic atlases. That's the sort of correct technical definition. Okay. Any questions? So let's. I think I just want to give examples of this. So the example 0, I will say just with words because it's kind of trivial. Just take an open set in Cn. Take an open subset of Cn, and you can construct an atlas with only one chart, which is the inclusion of the open set in Cn. And that's a complex manifold. So that's sort of the important but trivial example. So now let's do a non-trivial example. The first non-trivial example, and it's the two-sphere. This is. Do we have like the spray to? Okay.
Yes. Right, that one I'll get some spray if that doesn't work.
So the first example I want to discuss is the two-dimensional sphere that has a quite a natural structure of a complex manifold. So this will be like example 1. So let's consider the two-sphere. Okay. So we know this topological space is. Thanks, Max. Yeah. This. Thanks.
This is
you.
any better.
I should try to avoid this marker. So a two-sphere is the set of points, let's say x, y, and t in R3, such that the x squared plus y squared plus t squared is equal to 1. So this is a subset of R3. And then I want to give this this is a topological space. So I want to give this a sphere the structure of a complex manifold. So I want to define this atlas with holomorphic transition functions. So then how do we find this atlas? So we'll use what's called stereographic projection. So we'll use stereographic projection. So let's let n be the North Pole. So this is 0, 0, 1. And then we can do stereographic projection from the North Pole to the equator, the xy plane. So if we have like so here's the North Pole. So if we have a point in the sphere, so this is in 3D dimension. So what the stereographic projection, what it does, it connects with a line, considers the line that joins a point P in the sphere, say x, y, t in the sphere, and we look at the line connecting x, y, t and the North Pole, and this line will hit the xy plane at some point, and this is what we call the stereographic projection. So this is what we sigma n of this point. Okay, so this sigma n stereographic projection is a map that goes from the sphere minus the North Pole to the plane, to R2, and it is an homeomorphism. So it is continuous and it is a bijection. So, and then, so we're almost there. The only problem is that we didn't cover the whole sphere, so we need to cover, we are missing the North Pole. So what we do the same thing from the South Pole. From the South Pole, S2 minus the South Pole. So from the South Pole, we can do the same thing. We just look at the line that connects the point with the South Pole and look where that line intersects the xy plane somewhere. Yeah. So this will be C1. Okay. R2. And then, yes.
Sorry, I'm just wondering, so I'll use the North Pole one as an example. You say it takes steam, but this two-sphere without the North the origin in that case?
Here, if we look at the stereographic projection from the North Pole to the XY plane, so the 0 is the image of the South Pole. So if you connect the South Pole to the North Pole, that goes through the center of the sphere and hits in 0. So, but the North Pole is somehow sent off to infinity, because as the point gets closer to the North Pole, this line starts becoming like sort of parallel to the XY plane. So this point goes off to infinity if you approach the North Pole. So now these are two open sets on the sphere. They cover the sphere, and then hopefully the transition map is holomorphic, hopefully. But then actually the transition map is not holomorphic. That one is up to a minor thing, up to conjugation. So how do we calculate this transition map? So first, well, R2 I want to replace R2 with the complex numbers. Let me write formulas first for these maps, and then what is the stereographic projection of the point x, y, t? So there should be a formula here. And what is the stereographic projection from the South Pole, x, y, and t? So it's not hard to write the formula. So the key observation is like this. So if this is like t, and this is the radial variable, so this is like the distance to the t-axis, then if you have a point, so this point has coordinates, let's say r and t, then the stereographic projection will have some other coordinates, like you want to know what is the stereographic projection, and the key observation is like this: is that you have a triangle here, right angle triangle, right angle. So this is, if this has coordinate t, this is like 1 minus t. Is the distance from this to the North Pole. 1 minus t, and then this right angle triangle is similar to this bigger triangle, because they're both 90 degrees and they share a common angle. So this, and then if this is r, then the r is scaled here by a factor of 1 minus t, scale up. So this distance here is like 1 over 1 minus t times r. So then this formula here is like this: is 1 divided 1 minus t of the point xy, and for the South Pole for the South Pole, well, the only difference now is that again we have the two triangles. So, but now we have this bigger triangle and the smaller triangle. So the bigger triangle has this the long leg of the big triangle is 1 plus t, and then we scale it down to size here is 1, and this we scale it down by 1 plus t. So this point here here is like 1 over 1 plus t r. So 1 over 1 plus t x, y. So these are the formulas for stereographic projection. And now we want to do the transition map. So we want to know what is this. We want to calculate the transition map. And so to calculate the transition map, let me just do the calculation now with the complex numbers. So so R2 is the same as C, and this is just I'm identifying R2 with the complex numbers, the standard identification. So this is x divided 1 minus t plus I y divided 1 minus t, and this one here is 1 plus t, and then x plus y. Okay, so let's say now that we have a point in the intersection of these two open sets. So let's say that this P is a point is in S2 and is none of the poles. So then we have these two complex numbers. I will call these complex numbers Z. And I will call this complex number W. And then what happens if I do the product of these two complex numbers? So if I do Z times W, well, I will get something. You can just do the calculation. You have these two complex numbers. But here is where this subtle point comes, is that you actually, it's better to take complex conjugate in one of them. So what we do is we take complex conjugate, let's say of the south pole. So we take complex conjugate. So then complex conjugate, it changes the sign of the imaginary part. So then this thing becomes a minus. And when you do that, then the calculation becomes much better, because you do x plus, you have a number here and you multiply by the complex conjugate. So then you have x squared plus y squared. And then here 1 minus t times 1 plus t, this is 1 minus t squared. But then because the point x, y, t is in the sphere, x squared plus y squared is 1 minus t squared. So this is just equal to 1. So then this tells you what is this transition function. So if we start with Z, then do the inverse of by stereographic projection from the North Pole, you get this, and then use the stereographic projection to the South Pole, you get W, but W is 1 over Z, so this is just the function 1 over Z. It's 1 over Z. So remember here, there's the complex conjugate. Okay, so then the conclusion is that we have a holomorphic, the function 1 over Z is a holomorphic function. So it's a holomorphic function in the puncture plane, which is the domain of definition of the transition function. And this atlas, this is a holomorphic atlas. So we have S2 minus the North Pole with the stereographic projection from the North Pole, and S2 minus the South Pole with a complex conjugate of a stereographic projection. So this is a holomorphic atlas. So the two-sphere is a complex manifold with this atlas with two charts. Okay. Okay. Any questions on this example? Okay. So let's do an example in higher dimension. So here, this is a complex manifold. It's of dimension 1. So 1 is because it's C. So the complex dimension is always half of the real dimension. So it's a complex manifold of dimension 1. These things are known as Riemann surfaces. A Riemann surface is a complex manifold of dimension 1. So this is a Riemann surface, and this in particular is called the Riemann sphere, this complex manifold, the Riemann sphere. So let's do now an example in higher dimensions. In higher dimensions. The next example I want to discuss is a complex projective space, which is a sort of the sphere, the analog of the sphere in complex geometry. So we discussed the two-dimensional sphere, but in higher dimensions, spheres are not complex manifolds. So
So can I ask you, is the atlas in which you take the complex conjugate of the other stereographic projection compatible with this one or not?
right. We need to take a complex conjugate of one of these two to get a holomorphic atlas, yes. Otherwise it's not holomorphic. Otherwise you will get a 1 over Z conjugate, and that's not holomorphic.
Yes.
So, yeah. So, because actually, if you just take this without doing conjugation, this this atlas is not even preserving orientation. This orientation reversing is what, and they swap the orientation of the sphere. So you need to conjugate one of them. So, yeah.
Just one question. If you consider given dimensional smooth manifolds, can there always be a holomorphic chart?
That's a good question, and the answer is no. The four-dimensional sphere doesn't have any complex structure. They are like topological abstractions for smooth manifolds to admitting, to admitting complex structures. Actually, something called almost complex structures. They give you abstractions on there is you use topology to prove those things like characteristic classes and sort of things. That a good question. And not every smooth manifold, even dimensional, orientable. They have to be orientable because holomorphic maps they do preserve orientation. But there are some sort of topological abstractions. So and you also need to be careful because in most cases, if you have a complex structure, in most cases you will have many other which are not equivalent. So the same manifold can admit many different complex structures. Actually, maybe I should do this example. It's called elliptic curves. That's a good example to illustrate. Example. I was doing another complex projective space, but this example is also important. It's called elliptic curves. Elliptic curves. So here, just take like two numbers, omega 1, omega 2, two complex numbers, non-zero, and the ratio is not real. So they are linearly independent over the real numbers. So then out of these two numbers, you can form what's called a lattice. So this is Z times one of the omegas, direct sum Z times the other omega. So what this is like, so if this is omega 1, let's say, and then omega 2 is somewhere here. So this lattice, or what it does is just, okay, if you have omega 1, consider all the integer multiples of omega 1, and then you translate also with omega 2, or you translate upwards, downwards, and you obtain this, what's called a lattice. So this is an additive subgroup of the complex numbers of well, rank 2 or something. So it's a copy of set 2 inside C. And then you can define M sort of as the quotient. So this is the quotient of C divided by this lattice. So here what I mean is that I identify point Z with the translate of Z plus lambda with any lambda in the lattice. And then I consider the set of all these equivalence classes. So then a fundamental domain for this action is just a parallelogram. And then what I obtain as a topological space is always a torus. So this is always a torus. It's homeomorphic to a two-dimensional torus. So this is a circle times a circle. But as complex manifolds, they are not the same. If you change these omegas, they're all sort of different. So going back to the question, you have manifolds that don't admit complex structures at all, and you have manifolds that admit many different, generally different. Okay. I keep forgetting which is the dot marker. So now, okay, this is elliptic curves. Again, our example of Riemann surfaces because it's a complex manifold, dimension 1. And then now we want to discuss CPN, complex projective space. This is example 3. Complex projective space. So this is the notation is CPN. So as a set is just this is a set of lines through the origin in Cn+1. So when I say line, I mean complex lines. So these are complex vector subspaces of Cn+1 of dimension 1. So that's just as a set, but this set has a natural topology. So the topology is like this: it's Cn+1 minus the origin. It has a natural projection map because. If you have a vector non-zero, it spans a one-dimensional subspace. So you send that vector to that subspace. And then you have this quotient topology. Quotient. So this sends a vector set naught up to set n. So here I'm using this sort of convention that here is capital sets, because these are not really like coordinates on a manifold. These are like these coordinates on Cn plus 1, these capital sets, and this the equivalence class is just denoted with bracket sets set naught up to set n. So that's the equivalence class of the vector. So the line that the vector spans. And then this is a topological space with the how is it called? Like, the topology induced from this projection. Quotient topology. Yeah, thank you. Quotient topology is this topological space. It's a compact topological space because the sphere, the image of the sphere, the unit sphere in here covers all of it. So it's the image of a compact. So it's a compact topological space. And then this has a natural cover. It has a standard cover, CPN. You can cover with these subsets. Let's call the subsets UI. Is the sets of points set naught up to set n, such that the ith coordinate is non-zero. So this is so this we have like n plus 1. So n plus 1 open sets. So these are open. And they cover the whole space, because if you have a point in CPN, at least one of them has to be non-zero. And then we can define charts. So phi I goes from the set UI to Cn. It takes the point set naught set n. We will map it to, what we do is, well, we know that the I coordinate is non-zero. We can divide by it. We can divide by the I coordinate. So we send set naught, divide by set I. Oh, sorry, here is not bracket, it's just a normal. This is a point. This is a point in CPN. This is a point in Cn. So here I divide by the I coordinate. So, but then the ith coordinate you can omit, because you know that it's going to be 1. So you skip the I. So you jump from I minus 1 to I plus 1. So these are the charts. And so more, there's a geometric mean on this chart. Is like, let's say this is a picture of Cn plus 1. Let's say that this is the coordinate set naught, and here are all the rest of the coordinates, set 1 up to set n. So what we are doing is just we look at when the coordinate, in this case set naught equals 1, and if we have a line, we are just looking at the point of intersection of the line with this affine space. So the coordinates of this point, the coordinates of this point will be 1 or set 1 or set naught up to set n or set naught. So if we have any point on this line, and then so you see that the inverse, so let's say the inverse is also very easy. You just plug in a 1, so let's say phi naught minus 1 of a point set 1 up to set n. So now this is little sets. This it's just the point that plugs in a 1, and then Z1 Zn. So then, if you do the composition, so let's say if you do, for example, like phi 1 compose phi naught minus 1 of Z1 up to Zn. So, well, you need to divide this by, here you plug in a 1 on the first entry, and then you divide by Z, by this entry here. So this is just, well, another step. So this is phi 1 of 1 Z1 up to Zn, and phi 1 divides by this coordinate, the one that has the Z1 in there. So you obtain 1 over Z1. Then we skip the coordinate that we will need 1. So then we'll pass to Z2 divided Z1, Zn divided Z1. And again, this is holomorphic. This is same. In the domain of definition, the common domain of definition of this map is where this coordinate Z1 is not 0, and then it's a holomorphic map. So then, if n is equal to 1, CP1, so this is complex manifold of dimension 1, then if you follow this, you have only 2 charts, and the 2 charts are glued together by the transition function 1 over Z. So this is just the same as the two-sphere that we discussed. So this is just the same as the complex structure we define on the two-sphere. So interesting. Okay. Okay. So now I have until 3:50. 3:50. Okay. So. Any question? So, okay. So this example CPN is really very important. This is I don't know this, but just to motivate you, if you do physics, like some people actually use CPN, like doing there is something called like quantum geometric quantum mechanics. It's like if you do like quantum theory or something, this thing Cn plus 1 is like Hilbert space, and then there is a space of states. But the states, if you multiply by a constant, by a scalar, the state is the same. And then, so the actual space of what's called pure states is CPN, and that's what it is. But actually, CPN has a very rich geometry that we'll see, Fubini-Study metric, that is actually is related to this to quantum mechanics, because it sort of measures a sort of a transition probability between two different states. So this is an important example. But so far I haven't said many examples. So, and now the next one is really a huge class, because it's projective manifolds. The next is really like so it's more than an example, it's sort of like a subject, it's called. It's basically algebraic geometry. So projective manifolds. So now, if we have like sort of polynomials, let's say fi, so these are polynomials in these variables set naught up to set n. And I will require these polynomials to be homogeneous. So this fi is e.g. what does it mean homogeneous? So fi is a sum of monomials. It's a sum of monomials. So let's do, I don't know, let's do with Z1, Z2. It's a sum of monomials, but all these monomials, they need to have the same degree. So let's say Z naught cube plus Z1 square plus Z2. Well, this is not, but then if you, I don't know, Z naught square and then Z1, this is, so this is homogeneous. So, and then what is the example? Well, we want to consider the zero set of all these polynomials. So fi, the common zero set. So let's say that we have, let's say, k polynomials. And this requirement that the polynomial is homogeneous implies that these zero sets are sort of well-defined sets in CPN. Because if the polynomial vanishes at one point, then it will vanish at every scalar multiple of that point by homogeneity. So this is actually a subset of CPN. So these subsets are called like projective varieties. Yeah.
Sorry, so what are the, have we fixed a family fi of, and I'm a little bit confused about what the fi in that last equation are.
Right. So, okay, sorry. So let's say we start with the family. So we start with k polynomials, f1 up to fk. We start with k polynomials. And then we consider the common zero set of all these polynomials. So then the common zero set of these k polynomials is what's called a projective variety. But in general, this can be sort of a singular varieties. They can be like, I don't know, planes intersecting or sort of different things, not manifolds. But if you want a manifold, you need to require that this is sort of smooth. And if it's smooth, then it is called, yeah.
So all of the fi's homogeneous to the same degree?
Not necessarily. Yeah, they can be different, yeah. They can have different degrees, yeah. You know that, yeah. Yeah. So then, well, the most basic example is just one polynomial. Let's say, I don't know, let's be concrete. So let's say that n is equal to 2, so we're in CP2. And let's say that f of Z0, Z1, Z2, let's write an homogeneous polynomial. Z1 d plus Z2 d. So here d is any integer, let's say greater or equal than 2. Yeah. So that's an example. So we can look at the zero set of f equals to 0. So this is a polynomial in 3. So the zero set of this is some set in C3. But because the polynomial is invariant, so the zero set is invariant by scalar multiplication. So the zero set is actually becomes the zero set in CP2. And in this case, what does it mean smooth, the smooth condition is just that the 0 is sort of a regular value, so it's that smooth. What means is that there is no point, and there exists no point. Let's say Z0, Z1, Z2 in C3 minus the origin, such that all the partial derivatives vanish. Partial of f with respect to Z0, partial of f with respect to Z1. So that's the, if this condition is met, then the zero set in projective space is smooth. The zero set in C3 is always singular because the origin is always a singular point. Yeah. So, here. Sorry. What is it? Oh, the zero set. Oh, yeah, I think, yeah, there is this Euler identity. So this is equivalent that, yeah, you don't need to, I could also, yeah, you're right. In general, I should say f equals to 0. But if all these two conditions are met, f is also, but yeah, we can also add that, yeah. But anyway, for generic choices of polynomials, these conditions are met because it's like you have too many, you need at least one partial derivative non-zero. So if all the partial derivatives are 0, it's like each equation for a partial derivative is one equation, and you have like the same number of equations as variables. So in general, for generic choices, the only solution will be like 0, 0. All these hypersurfaces will intersect just at 0, 0, 0. So, but anyways, this is a sort of a generic condition for generic choices of polynomials. This will happen. So in particular, it happens for this one. So you calculate the partial derivatives, and you see that the only, if the partial derivative with respect to Z0 vanishes, well, Z0 has to be 0. If the partial derivative with Z1 is 0, well, Z1 has to be 0. So the only set where the 3 vanishes is just the origin. So this is a smooth. So so this particular example is a smooth. So this 0 set M in this example is a hypersurface in CP2. It's just again, it's a Riemann surface again. So M. So this is a Riemann surface. Riemann surface of genus. So of genus, there is actually a nice formula for the genus. It's called the degree genus formula. The genus is, you can calculate the number of poles in the Riemann surface from the degree of the polynomial. So V equals 1, well, that's kind of a trivial case. It's just CP1 because it's just a linear. Well, V equals 2, you again, genus 0, so again, it's a Riemann sphere. And V equals 3, you got these elliptic curves, genus 1. So, okay.
So,
yeah.
Just out of curiosity, do we have a regular integrator for complex manifolds?
Yeah, I'm sort of implicitly using that, yes. Sort of, but yeah.
And the conditions are the same as the one for manifolds?
The same for, yeah, that's correct. And sort of, yeah. I'm implicitly using that saying, if these conditions are met, then the thing that you obtain is a complex manifold. This follows from the implicit function theorem for holomorphic functions. Thank you. Yeah. Okay. So now, so we are still with examples, but this is a huge class of examples. It's like, well, it's basically, and I think all interesting examples are sort of this kind. So, and then so then example example 4. So well, we'll go back to some sort of a trivial thing, but you can do products. Products, there is an obvious way of, if you have two complex manifolds, you do the product of n1 times n2, n1 times n2. So the dimension is the sum of the dimensions. So, for example, CP1 times CP1. And that's a complex manifold of dimension 2. Dimension 2 is called a complex surface. It's a complex surface. And funny thing is also is of the same kind of this projective manifold. So CP1 times CP1. So we have the x0, x1. These are the point in CP in one factor. We have y0, y1 is a point on the second factor, and we can map this to the following. So we can do the following. We can do x0, and I can multiply with this, let's say y0, x0, y1, and then I do the same for the x1. So x1, y0, x1, y1. So this is a point in, so I have 1, 2, 3, 4. This is a point in CP3. And this, the image, so this is a map. This is an example of a holomorphic map between complex manifolds. And then the image of this CP1 times CP1 is a hypersurface. So if you see, if Z0 is this coordinate Z0, if you multiply Z0 and Z3, so then you get the x0, x1, y0, y1, and that's the same as multiplying the ones which are in the middle. So this is Z1, Z2. So we have is the same. So the image is this hypersurface in CP3, and it's actually a biolomorphism. So it's an equivalence of CP1 times CP1 with this hypersurface of degree 2 in CP3. So that's called, how is it called? Segre, thank you. Segre embedding. So, and here again, I will try to make a connection with physics, because if you just go to Wikipedia and search for Segre embedding, it says something like very curious. But I need to read from Wikipedia. That's it. So Wikipedia applications. It is a natural map. It is Segre embedding, describing non-entangled states in quantum mechanics and quantum information. So it has some applications. I don't know. So okay, then. But the point that I introduced the example is because this product is actually one of these projective manifolds. It's a hypersurface in CP3. So now, to really understand the difference between complex manifolds and smooth manifolds, like real manifolds, I think the best way is more clear, more evident that these two categories are different when you look at the morphisms. So I sort of didn't define what are the morphisms between complex manifolds. Morphisms are just holomorphic maps between complex manifolds. So then the definition. So if you have M N. So these are complex manifolds. And we have, let's say, some continuous map. Continuous. Then is holomorphic. If whenever you have coordinates, if you look in local coordinates or charts, this is holomorphic. In its whenever it is defined in its domain of definition. So this becomes a map from Cn to Cn. So, or well, these are allowed to have different dimensions as M, N. So it's a map between from an open set in Cm to Cn. So it makes sense to ask it to be holomorphic. Well, and these are just charts. So psi here, I guess psi is a chart for M, and the other one, let's call V, is a chart for N. So these are the morphisms in this. And now, this. I just want to mention some results about this that make evident that these complex manifolds behave very different than a smooth manifold. Some results. So one is that let's say M is a compact and connected complex manifold, and then we have a holomorphic function, and C is holomorphic. Then this function f is constant. So this is a result, which is actually not hard to prove. It is because these holomorphic functions, they obey the maximum principle. So maybe you know from one complex variables in one dimension that real and imaginary parts of holomorphic functions are harmonic. And in higher dimensions, the same holds. Real and imaginary parts of holomorphic functions are harmonic. In fact, something much stronger called pluriharmonic are harmonic in all complex directions. But they obey, in particular, holomorphic functions obey maximum principle, so they cannot have local maximums or minimum. So this is a huge difference with the smooth case. If you have smooth manifold, you have plenty of smooth functions on it. So that's one case. And another is that we can consider this the automorphism groups. So let's say now that M is compact manifold, and complex manifold. Then we can look at automorphisms of M. So what is this? So these are maps F go to M, and which are holomorphic bijections. So F is holomorphic, and F minus 1 is also holomorphic. So in the category of complex manifolds, two complex manifolds which are biholomorphic, so that means that there is a holomorphic map with a holomorphic inverse, they are considered sort of the same. And then in particular, if you have a complex manifold, you can look at the group of automorphisms, so self holomorphisms of M with itself. And the result, this time the theorem becomes a non-trivial. The theorem is that this is sort of a finite dimensional group. It is a Lie group, yes. It is a finite dimensional Lie group. Yeah. Yes, it is.
And is it a complex issue?
I think so. Yeah. 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 So the way I think of this Lie group, if you look at the Lie algebra of it, so the Lie algebra is the set of holomorphic vector fields. What is that? Holomorphic vector fields are sort of holomorphic sections of the tangent bundle, and the main result is that this set of vector field is a finite dimensional vector space. And the general reason is sort of a PDE theory, because it's sort of like a del bar, these holomorphic sections, they satisfy the equation that they are holomorphic, and this is sort of the del bar equation for the sections is sort of an elliptic, and the kernel is finite dimensional. But it's sort of a deep result. It's sort of a deep theorem. But this is again huge contrast with differentiable manifolds, because you have a smooth manifold, you look at the diffeomorphisms of the manifold, and is in general is something super complicated. Even the case of the circle is super interesting, like it's related to Virasoro algebras or whatever. It's super, and in general it's something that we just don't understand at all. And this is a big difference. In particular, I work on the subject of Kähler-Einstein metrics. And then this makes a huge difference in the topic, because Einstein manifolds, like the Einstein equations, are invariant by diffeomorphisms. And then there is no way this can be an elliptic system, because you have infinite families of solutions, because if you have one, you have diffeomorphism, you have another one. So it's just very difficult, and there are techniques to handle with these things, but it's complicated. But then Kähler-Einstein manifolds are Einstein metrics and complex manifolds. You reduce the symmetries from diffeomorphisms to biolomorphisms, and then you reduce sort of to finite dimensions, and the equations are elliptic, and everything is good. So this is again a huge difference. And so now. Any questions?
Is there an upper bound for the dimension of this group in terms of the dimension of
Right. I really don't know. I think so. But I think so. But I don't know now. I think so. I think you might be the same with isometries of a Riemannian manifold, the same kind of bound that you get with isometries of the Riemann. But so then not only that, not only for compact manifolds, but also for some non-compact manifolds. Also, this group of automorphisms is quite often it is finite dimensional. So for example, so here's an example. So we have the unit ball in C2. So this is the unit ball. And then you can consider that the disk, this time the disk, again in C2. So this is the product of the disk is now the disk in the complex numbers. So we have these two open sets in C2. And in this case, the group of biolomorphisms of the unit ball with itself. This is the unitary group of 2, 1. I don't want to explain, but this is sort of like this is a group of, you have a Hermitian form in 3 complex dimensions of signature 2, 1, and you look at the sets of linear transformation that preserve that Hermitian form. The P stands for productization. But this is related to complex hyperbolic geometry that I won't talk about. But the point is that one can prove this, that this is the group of biolomorphisms, and then the group of biolomorphisms of the disk times the disk is different. So it's the group of automorphisms of the disk is SL to R. So square, because you have 1 for each factor. But then you also can like sort of there is an obvious automorphism. The most obvious is you can just swap. So this makes the group sort of a semi-unit product. So you have a swap map, but the thing is that this group is sort of a connected group. This group is 2 groups. It has 2 connected components. So then they are not biolomorphism. These 2 sets, even if they are clearly diffeomorphic, they are not biolomorphic. They have different automorphism. So
what's the group so is that SL2R?
yeah, I think I will explain that because yeah. So then I think I will mention a more basic example of biolomorphism. So example of biolomorphism. So we can consider these 2 sets H. So this is the upper half plane. So this is the points in the complex plane that have imaginary part bigger than 0. And we have also the unit disk such that the absolute value of psi is less than 1. And then these 2 sets are biolomorphic. So the thing is that if you have so this is the upper half plane, this is H, and then you have the disk here. Then if you have a point in what is the upper half plane? Well, you have I and minus I, and the upper half plane is the set of points which are closer to I than minus I. So then, if you map a point here to, if you compare Z minus I with Z plus I, well, this is smaller, so this will have absolute value less than 1, so this lands on the disk. So, and this is a biolomorphism, so this has a holomorphic inverse, so this is an example of a biolomorphism. So from the point of view of complex manifolds, they are the same. And then, more generally, you have the Riemann mapping theorem. Riemann mapping. So it says that if you have any open set proper, so not equal to C, open, and simply connected, pi1 trivial, then this set is U is biomorphic to the unit disk. So, and here it's important that it's strictly contained, because C, I'll write it here, C is not biolomorphic, so C is not biolomorphic to the disk, and this is easy because if you have any holomorphic map from C to the unit disk, so if this is holomorphic, so it's a holomorphic function entire, so meaning that it's defined in the whole of the complex numbers, and because it takes values on the disk, it's bounded. So it's bounded. So then there is this reveal theorem says that this is f is constant. So these are again examples that are not biomorphic. Okay. Any question? Yeah.
So can you explain again what pi1 is?
Pi1. Yeah, this is fundamental group.
No, sorry, yes.
Fundamental group. So, okay, so any question? Okay, I think I will stop for today, because then today was all about complex manifolds, and tomorrow I will introduce this Kähler matrix and this complex manifolds. That's it.
Any final questions?
It's more of curiosity because we started with an Hausdorff
Yeah.
manifold, and in the smooth case, when we project even an Hausdorff smooth manifold, we can easily end up with something that is non-Hausdorff.
Right.
For instance, you can take the R2, the orbits that are horizontal lines, but one that is punctured
That is
zero,
true.
and you have R with the double origin in that case. Does the complex structure in this case give something stronger, or
No, I think you can have the same type of problems. Yeah.
you can?
I think I didn't bother in the example of CPN that I used this quotient topology. It is Hausdorff, but one has to prove it, I guess. Yeah. But yeah, the same.
Two questions?
And sorry, linking to this, the thickness and properness of actions in the quotients is the same as the smooth.
That's also true. Yeah, if you have a group acting freely and a complex manifold, the quotient is also complex. Yeah, that's true. Yeah. And actually, most Riemann surfaces are just quotients of C, the complex numbers, the disk, and the sphere, which is a particular case, the Riemann sphere. Those are all compact Riemann surfaces, are just quotients of these things.
Okay, thanks.
All right.
That's it.
Thank you.